Alright, we're going to talk some more about kinetics. So, in other words, how a faster reaction occurs. And what we're going to talk about today are rate law expressions. And so, this is going to be different than that equilibrium expression, although you might think they look a little similar. So, here we go. A rate law expression looks like this. We have rate equals K times the concentration of A to the X and B to the Y. A and B in those square brackets mean the concentrations. K is a rate constant. It's specific to a certain temperature. We'll talk more about that in a little bit. X and Y are exponents. They don't have any relationship to the coefficients in the balanced equation. They have to be determined by experiment. But we call those the order of the reaction. So since X is with A, X is the order of the reaction with respect to A, and Y is the order of the reaction with respect to B. And we'll talk a little bit about what that means here in a sec, but the overview is that if it's to the first power, that means that the rate is directly proportional to the concentration of that reactant. So doubling the rate doubles the concentration. Quadrupling the rate quadrupling the concentration quadruples the rate. A power of 2 means it's directly proportional to the square of that reactant, and a power of 0 means that the rate does not depend on the concentration of that reactant so long as some of it is around. And if we add up all our exponents, we get the overall order of the reaction. So, some examples. Here we have this equation. NO yielding dinitrogen monoxide and nitrogen dioxide. Well, it's all only dealing with our reactants, and we can say that this is first order with respect to the concentration of NO. Or sorry, I didn't look at my rate. That's a 2. That's second order. And it's second order overall. Okay, let's look at this next one. We've got our reaction. We've got our rate law. These are understood exponents of 1. So it's first order with respect to the concentration of NO2 and with the concentration of fluorine, which means 1 and 1 makes 2. It's second order overall. Alright, let's take a look at this third one. NO2 yielding nitrogen monoxide and oxygen. Our rate, we have NO2 to the second power, so it's second order with respect to NO2, and it's second order overall. Let's look at this third one. I have hydrogen peroxide, iodide, and hydrogen as my reactants. My rate law doesn't have hydrogen in there, so these are both to the first power. What that means is that hydrogen must be to the 0 power, because anything raised to 0 power is 1, right? So we can omit it ultimately. So again, it's first order with respect to the concentration of hydrogen peroxide and iodide. It's 0 order with respect to that hydrogen ion, and 1 plus 1 plus 0 is 2, so it's second order overall. Okay, so let's try a real life example. The gas phase reaction nitrogen monoxide and bromine to form NOBr is found to be second order in NO and third order overall. Write the rate law for this reaction. So we're going to have rate equals K, we're not talking about K yet, our two reactants, the concentration of NO and Br, bromine. It's second order with respect to NO, and it's third order overall, so that means bromine must be to the 1 power, and so you can leave the 1 there, or it's understood. Okay. Now let's think about what those exponents mean. So we have our hypothetical situation, A plus B plus C yields product. The rate law is determined to be rate equals K, A to the first, B squared, and C is not there, which means C is to the 0 power. Okay, what happens when we make the following concentration changes? And A, we double the concentration of A without changing the concentration of B or C. So rate equals K, some constant, times 2A, and B is still squared, and C is still to the 0th power. Well, I just multiplied everything by 2 because of this 2 right here, so the rate doubles. Okay. What happens if we double the concentration of B without changing anything else? Well, got K, A is still the same, it's to the 1st power. We've got twice the amount of B, and it's squared. C is to the 0 power, so we can leave it out. Well, 2 squared is 4, so the rate quadruples. Okay, write yourself a little note. Okay, what if we double the concentration of C without changing the concentration of A or B? Well, C is raised to the 0 power. Anything, no matter what it is, raised to the 0 power is 1, which means we will not have a change here. Okay. And D, what happens if we double all 3 concentrations simultaneously? So we have rate equals K, 2A times 2B squared, and then times 2C to the 0. Okay, well that's 1, that doesn't account to anything, but 2 times 2 squared, 2 times 4 equals 8. So the rate increases by a factor of 8. Alright, so let's try example 6 on your own. I want you to try that, think about it, and then we'll check our answers. So you can pause this for a sec, and then you can start it back up. Okay, the concentration of A is tripled, in which to the 1st power the rate is going to triple. If the concentration of B is halved, and to the 1st power the rate will be halved. But if we triple A and we half B, 3 times 0.5, rate is going to increase by 1.5 times, or 3 halves if you want to do that. Okay, last bit is how we would graph this. Okay, so concentration versus time graphs don't give us a very clear distinction with our 1st and 2nd order reactions. But if we graph rate versus concentration, then we see some really clear changes. And so that's what we're going to do. So we'll start with our 0 order reactions. If we have concentration versus time, we just get a straight line. But 0 order means that the concentration doesn't matter. And so we graph that and we would get a horizontal line. Now think about this from a mathematical perspective. If rate equals K times A to the 0, that's 1, then rate just equals K. Well, this is an expression where Y, whatever is on your Y, equals a given number. It's a horizontal line. Let's talk about 1st order reactions. So if we have concentration versus time, a 1st order reaction is going to look like this little slope. Pardon my artistic abilities. And rate versus concentration, well, doubling the concentration would double the rate. Tripling the concentration would triple the rate. So it's directly proportional. We'll get a nice straight line. Now, something about 1st order reactions is that they have a constant half-life. What that means is that it has a constant amount of time for the concentration of a reactant to decrease to half its original value. So I'm going to say, let's start out with a concentration of 100. Well, half of 100 is 50, half of 50 is 25, half of 25 is 12.5. And we'll call this time, so this is concentration, and we'll say in days. Okay, so I'm going to say 2, 4, 6, 8, 10, 12. So if I start out at time 0 with a concentration of 100, and then my data looks like this, do you see that it takes 4 days to go from 100 to 50? It takes 4 more days to go from 50 to 25. 4 more days to go from 25 to 12.5, and so on. So for this reaction, the half-life, T1/2, is 4 days. Okay, moving on. Second order reactions. If we have concentration versus time, we get a nice little slope that looks a lot like it did for the first order reaction. But for rate versus concentration, we get this. Because rate equals K, a constant, times A squared. Well, this is the graph of a line, X squared, same sort of thing. And so we can tell a lot from our graphs of rate versus concentration.